Look, nails hanging from a rock. Paper clips picked up by a piece of rock. What's going on here? Well, you are seeing a natural occurring magnet called magnetite, or a lodestone, in action. These rocks have the ability to attract certain objects with an invisible force called magnetism. It is thought that possibly 2,000 years ago, some ancient Greeks discovered by accident the ability of certain rocks to attract some metals. Maybe a farmer had a metal tool or spearhead magically stick to a piece of magnetite. They discovered this unusual effect in a part of Turkey called Magnesia, so the Greeks called the rock responsible for this attractive force magnetite. Today, we have permanent magnets that are used in hundreds of ways, from holding pictures on the refrigerator to producing electricity inside huge generators. It's fun to mess around with magnets. They come in all kinds of sizes, shapes, and strengths. Some magnets are round, some are bar-shaped, some are shaped like horseshoes, and some are donut-shaped. Magnets have two poles, a north and a south pole. Sometimes the magnet is colored to distinguish from north and south. These donut magnets are an excellent way to show how magnets attract and repel. When opposite sides of the magnets are facing each other, the magnets are attracted and come together. If the similar sides are facing each other, then the magnets repel or push away from each other. We can illustrate this with bar magnets as well. When the same sides are brought near, they push apart. However, when opposite sides are near, they attract or pull together. Magnets don't attract all objects. You can experiment with various objects to see what is attracted and what isn't attracted to a magnet. It might appear that objects made of metals are all attracted, but that isn't necessarily true. Only certain metals are attracted by magnets. These coins are made of metal, but are not attracted to the magnet. But this paper clip and these staples are definitely attracted to the magnet. You'll find that only metals made of nickel, iron, and cobalt are attracted by magnets. Magnetism can penetrate objects as demonstrated by this magnet moving the paper clip through the wood. If we put a bar magnet into a bowl of paper clips, we will find that most of the clips attach to the ends of the magnet. The magnets are just at the ends. We can see the lines of force around a magnet by placing a piece of glass or thin cardboard on top of the magnet. Then we sprinkle iron filings onto the glass or cardboard, and the little bits of iron line up along the invisible lines of force that are found around the magnet. We can view the lines of force created when the ends of two different magnets are brought near each other. Remember that unlike ends of magnets attract each other, and like ends repel. Let's look at the lines of force when unlike sides of two magnets are brought near. Now, let's turn one magnet around so that like ends are facing each other. You can see the lines of force are repelling each other. If we tie a string to a bar magnet and let it hang, it will rotate around until one end is pointing north and the other end is pointing south. The end of the magnet that points north is called the magnet's north pole, and the opposite end is called the south pole. The magnet lines up this way because the Earth is a giant magnet. It is as if a giant bar magnet went through the center of the Earth, as shown in this picture. The magnet isn't really there. In fact, scientists believe that the magnetic effect is caused by very hot liquid metals in the outer core of the Earth, creating electrical charges that cause a magnetic field to develop. The invisible magnetic field extends out into space, protecting the Earth against solar particles released constantly by the sun. This stream of particles is called the solar wind. These charged particles make contact with the Earth's magnetic field lines and travel towards the poles. As the particles make contact with oxygen and nitrogen atoms in the atmosphere, a beautiful show of lights in the sky is displayed. These are referred to as auroras, or the northern and southern lights. The ancient Chinese were the first navigators to use magnets to help them sail the seas. They found they could use natural magnets held by string as a method for identifying north and south. These were the first compasses. Later it was discovered that a needle or thin piece of iron could be turned into a magnet by stroking the magnetite across it repeatedly. This needle, suspended on a piece of bamboo or cork and floating in water, would rotate around until one end pointed north. Sailors could then determine what direction they were sailing in by comparing this needle with the direction of the boat. All matter is made up of atoms. Inside atoms are orbiting electrons that speed around the atom's center or nucleus. The movement of electrons causes a magnetic effect, and atoms develop a north and south pole. In most materials, the magnetic fields cancel each other out, so these materials have no magnetism. However, the atoms of iron, nickel, and cobalt are different. They have domains or groups of atoms that line up together, creating a magnetic field. Objects made of iron, nickel, or cobalt can be magnetized by stroking them with a magnet. You must stroke them in the same direction to get the atoms to align properly. A magnet made this way is called a temporary magnet. This iron nail is turned into a temporary magnet after repeatedly rubbing a permanent magnet along its length. It attracts the staples because the magnetic force in the nail causes the atoms of the staples to slightly line up with the nail's magnetic field. This creates a temporary magnetic effect in the staples, and they are attracted to the nail. When the staples are not free, they lose that magnetic effect. Magnets can be damaged and lose their magnetic ability if they are dropped or heated. Dropping causes the domains in the atoms to be jumbled around. They fall out of alignment, and the magnetic effect is lost. Heating can also damage a magnet. When atoms are heated, they move faster, and as a result, move out of alignment. In 1820, the Danish physicist Hans Ørsted discovered that electricity could cause a magnetic effect. During a demonstration, he brought a compass near a wire that had an electric current flowing through it. The needle spun in a new direction. He found this to be very unusual, as compass needles always pointed north and south. With further experimentation, he found that electricity flowing through a wire created a magnetic effect. An electromagnet can be made with some simple materials. An iron nail, some wire, and a battery can be used to make an electromagnet. Wind the wire around the nail. Attach the ends of the wire to the battery, and the electricity flowing through the wire creates a magnetic field around the wire and nail. The domains of the atoms in the nail are temporarily lined up to form a temporary magnet. When one of the ends of the wire is disconnected, the flow of electrons stops and the magnetism stops. Electromagnets are used in various ways. Doorbells use electromagnets. Notice the coiled wires and the way they attract the doorbell clapper when the electricity is applied. There are electromagnets in a phone receiver that change the electric signals into sound waves. There are electromagnets in many motors. This motor has magnets with a drive shaft between them that contains the electromagnets. Here's an experiment conducted at the Museum of Science in Boston to illustrate the power of an electromagnet. The power drill has been set up with a handle or crank in its bit. The batteries are removed, and instead wires are attached from the drill motor to a light bulb and to the coil of wire of an electromagnet. Using the crank, the electric motor becomes a generator, as demonstrated by the light bulb. You could run a series of experiments to test what factors affect the strength of the electromagnet. Does the size of the iron core affect the strength? How about the number of turns of wire? Or maybe the strength or voltage of the battery used will determine the strength of the electromagnet. Set up an experiment to test all these variables one at a time. After Hans Ørsted discovered that electricity created a magnetic effect, other scientists wondered if magnetism could create electricity. In 1831, Michael Faraday, an English scientist, set up an experiment that proved that electricity could be produced when a magnet was pushed in and out of a coil of wire. Notice that the needle, which illustrates the flow of electricity, only moves when the magnet first moves. Also notice that the needle changes direction as the magnet moves in different directions in and out of the coil of wire. Electricity produced in this fashion by a changing magnetic field is called electromagnetic induction. Faraday found that a greater electric current is induced if there are more coils of wire. He also found that if the magnet moves faster, the induced electric current is stronger. Faraday also discovered that it didn't matter if the magnet was moved inside a coil of wire or a coil of wire moved inside a magnetic field. In either situation, electric current is induced. At power plants, they use electromagnetic induction to produce electric current. In most large generators, a giant magnet is turned inside a coil of wire. Remember that the current electricity produced in this fashion changes direction continuously. This is called AC, or alternating current. A battery produces DC, or direct current. Direct current flows steadily in one direction. This train is traveling 355 kilometers per hour, or 220 miles per hour. That speed might seem impossible for a train, but that isn't the most exciting thing about this train. You see, this train is traveling because of electricity and magnetism. This is a maglev train. Maglev stands for magnetic levitation. As you know, opposite ends of a magnet attract and similar sides repel. This train is making use of these facts to race down the track. This is the German magnetic levitation train called Transrapid. It is designed to go as fast as 550 kilometers per hour, which is 342 miles per hour. There are magnetized coils running along the track or guideway. On the underside of the train are large magnets. When electricity flows into the guideway coils, a magnetic field develops. The opposing magnetic fields of the guideway and train lift or levitate the train about 1 centimeter, or about 1/3 of an inch above the track. Once levitated, the electromagnet coils in the guideway are used to push and pull the train along on a cushion of air. Because the train is floating, there is no friction between the train and track, which allows the train to reach unbelievable ground transportation speeds. This form of transportation has been in development since the 1970s. Look at this maglev demonstration model. The device is easily suspended in midair because inside are 2 donut magnets that are repelled by magnets in the base. With a little twist, the device spins effortlessly. There is only one place where contact is made, so the friction is minimal. That's why the device spins for such a long time. With little friction between the moving parts, the device can continue to spin for long periods of time. Now it is time for the program quiz. There are 5 multiple-choice questions. Question 1. If 2 magnets have opposite poles facing each other, they will be what? A. Repelled. B. Attracted. C. Neutralized. D. Opposed. Question 2. If 2 magnets have the same poles facing each other, they will be what? A. Repelled. B. Attracted. C. Neutralized. D. Opposed. Question 3. What are controlled by electricity? A. Lodestones. B. Pieces of magnetite. C. Electromagnets. D. Permanent magnets. Question 4. Iron nails can be made into magnets because of their what? A. Domains. B. Lodestones. C. Magnetite. D. Protons. Question 5. Magnets are used in electric motors and what? A. Horseshoes. B. Lodestones. C. Turbines. D. Generators.